Assalamualaikum and selamat sejahtera. In the last video, I have explained how to sketch voltage and current waveforms of single-phase uncontrolled rectifiers with resistive loads. This time, we will analyze the waveforms based on the general parameters of the rectifiers. Before we start the analysis, it is good to consider the ideal waveforms of the output voltage and output current of the rectifiers. The black line and the red line are referring to the ideal waveforms of the output voltage and output current respectively. These waveforms are called ripple-free waveform, and they represent the average or DC components of the AC supply converted by the rectifier. Unfortunately, without any filters, the rectifiers can generate the ideal voltage and current waveforms. In the last video, we have seen that the output voltage and output current waveforms generated by both half-wave and full-wave rectifiers are not constant. These waveforms consist of voltage or current ripples due to the existence of AC components at different frequencies. Based on Fourier series, the AC components are called harmonic components. Usually, when we want to design a filter, we can use the information related to the harmonic components. Other than that, the ratio between the harmonic and the DC components represents the ripple factor of the waveforms. Ideally, the ripple factor should equal to 0. Moreover, the rectification ratio or the efficiency of the rectifier is also affected by the ripple waveforms. In ideal condition, the efficiency of the rectifiers is 100%. Now, let's analyze the output voltage waveform of a single-phase uncontrolled half-wave rectifier. First, we start with the calculation of the average output voltage using this general equation. According to the equation, we need to determine the full period of a complete cycle of the output voltage waveform. Based on the wave shape of the output voltage, we can identify that the full period, which is T, is equal to 2 pi. Hence, we can rewrite the general equation by replacing the T with 2 pi. However, since the area under the graph can be calculated between 0 until pi, therefore, this T should equal to pi only. Based on a complete derivation of the equation, therefore, the average output voltage is equal to Vm per pi. Next, we can sketch the waveform of the average output voltage as follows. To find the RMS output voltage, we can use this general equation. Based on the final equation, we can see that the RMS output voltage of this rectifier is equal to half of the peak amplitude of the output voltage waveform. Thus, we can sketch the waveform as follows. Next, we can use the average and RMS output voltage values to calculate the ripple factor of the waveform. By assuming that the peak amplitude is equal to 1, therefore, the percentage of ripple factor is equal to 121%. Meanwhile, the efficiency of the rectifier is only 41%.